Hi, everyone. So after the British accent, we will get the French accent. So we are glad to be here to share how we leverage Anyscale and LLMs for our catalog onboarding features at Mirakl. I'm Mathieu Minou, Principal Architect.
And I'm Arthur Delettre, Manager Data Science at Mirakl, and we are both based in Paris. So, before diving a little bit into the details of the technical implementation, let's get a little bit of context. So Mirakl, we're a software editor that implements a software that is used by our operators, meaning marketplaces, to operate their marketplace, meaning they will be able to operate their sales, their sellers, but also manage their catalog. So we were founded in 2012. We have more than 800 employees and a lot of clients. So our clients are the likes of Macy's, Decathlon, Romelin, but we also have some B2B marketplace clients such as Conrad and Airbus. So the problem we're going to talk about today is what we call the catalog onboarding. So basically, when you're a seller on a marketplace, before you're able to sell your product, you have to onboard them into the marketplace. So as a seller, you will have you will have your catalog, which is basically a product listing that is defined in your own format. So basically, this can look like this, where you have a big Excel file with a line is one product, and all of the columns are the attributes for every product. And this is very custom for every seller. And basically, a seller, before selling to a marketplace, is going to have to put all of this data into the marketplace's data model, meaning categories, then for each category, some attributes, and also a lot of validation on attributes. And this format is very custom from one marketplace to one another. So basically, if I'm a seller and I want to onboard my big catalog on one marketplace, it's going to be days and weeks of data mapping before I'm able to sell. And if I want to sell on another marketplace, let's go again, weeks and weeks of work. And basically, they have to do this all around, and they have basically dedicated teams to do this very redundant and really hard task. So that's what we're trying to solve. And to frame a little bit the problem, so I talked about weeks. We've been able to measure this at Mirakl in terms of time. So basically, taking historical data, we often see that on average, a seller takes about 28 days to come up to a marketplace and to be able to sell. And more than half of the time is used for the catalog onboarding, basically those data mappings and lots of manual stuff. So that's a really big problem to solve for us. And so, without giving you a lot of details of the iterations that came year after year, today we are going to talk about what we are building today, which is named the Catalog Transformer. And basically, the Catalog Transformer is what we call an AI-powered software for product import. So basically, it was thought around the seller experience so that it is the easiest as possible to use to the seller, and that it provides the maximum autonomy, so that it allows the seller to have everything done automatically in the back. So basically, as a seller, I'm able to drop my CSV file here. It can also be used via API. And I can basically select the catalog transformer as my product onboarding method, as well as choosing some of the options. So namely, the first one, for instance, is the rewrite content option, where you can say, OK, I want the catalog transformer to rewrite my titles and my descriptions so that they can match what the marketplace expects and be more SEO-friendly for better referencing. But we also have other enrichments. And at the end, the seller can choose to preview the result of the transformation. So he will have the product listing put into the marketplace format and still be able to do some manual correction on some things, but we expect the process to be like 99% done. So that's the catalog transformer. And as you might expect, this process relies a lot on LLMs because we want to extract attributes from raw text. We want to do a lot of things that are very generalistic, but also really hard. And those are tasks that we were not able to do before LLMs. So the first problem we had to face before releasing the catalog transformer was the scale. Because when we were looking at historical data, we saw that we were onboarding a little bit more than 10 million of products each month. And this was only growing. We were back in 2023. And so by taking a look at the first pipeline, we saw that this was representing more than 70 billion input tokens and 25 billion output tokens. So this is basically a massive workload. And doing some cost estimations at the time, we saw that using an API like GPT-4 would end up costing us more than $500,000 per month. So that's really huge for an enterprise of our scale, and we were expecting the volume to only go rising. And so what we did is we did a little experiment on smaller models, so the LLaMa 3.1 8B, and basically those allowed us to achieve a cost that was much more, well, great for us because it was not that much expensive for the volume. So we already knew that even with API cost plummeting over the time, we would have to target small LLMs if we were to achieve really big scale. And so what we did is we took the best of both approach to have a different way to build it in the time. So first, we look at the GPT-4 method, which was basically really strong out of the box, and the implementation was really easy. We didn't have to care about the hosting because it was basically handled by OpenAI, and we used it to basically build a beta with a smaller set of sellers that were able to give us user feedback. So basically, we built the feature and the functional scope around this, and then we already knew that to get a very big cost competitiveness, but also to be able to customize the system, to reduce the hallucinations, to ensure consistency, we would have to target fine-tune small LLMs for the production workload at scale. And another thing we added to the system is what we call the layering. So basically, the layering is we witnessed that the small LLMs that we fine-tune were really great at working on in-distribution data, but not that much on out-of-distribution data. So for instance, those exotic cases can be foreign languages that we've never heard of or something like this. And so what we did is a layering method where we take the best of both models. And so basically we have a router that redirects the biggest part of the volume to a small model. So this allows us to have an overall competitive costs, but we still use really big models for a fraction of the volume to be able to ensure the quality of the results overall. And this also has other uses that we will talk just after. And just before diving into the infrastructure, how did we fine-tune the small specific LLMs? So basically, we use supervised fine-tuning, which is basically the same as what you do on a lot of other AI use cases. So we provided an LLM with product data, so stored as prompt, and what we expected as the response for those. And basically, we trained what we call the LoRA adapters of the LLMs, which is basically a small subset of the weight of the model. And this is basically the customization of the model. And then we were able to apply this model to the inference workload and to basically get the predictions for the new incoming data. So I'll let Mathieu talk about the infrastructure.
Okay, so I'm going to to walk you through how we implemented the inference of LLM and how we validated our approach with a proof of concept. But first, before choosing a solution, I have to define the constraint, the Mirakl constraint for this project. So the first one is the most important one, the pricing. Like Arthur said, at production scale, the price with OpenAI's model will be $500,000 per month, and that's simply not sustainable. The second one is the scalability and the reliability. Like I said, we used GPT models served by OpenAI, and in Q2 2024, we noticed outage, especially during the US business hour, and that's not possible for a production system. We also want to support a system that supports private model that we store on Hugging Face, and also, like Arthur said, the support of LoRA adapters. We want a solution that is easy to run and to operate. We don't want to manage new infrastructure or to set up a new Kubernetes cluster. We want something that is simple, so no self-hosted. If possible, a multi-cloud service, because we provide, at Mirakl, we provide our service to our customer on multiple cloud providers, because some of our clients are direct competitor of Amazon. We also want something that is configurable as code, because we do that for each of our projects at Mirakl. Everything should be historized, reproducible, and automatized. And the last one, a bonus, is the integration with Datadog, because that's where we store all our metrics and we monitor our application. So we shortlisted in 2024 3 solutions: Google Vertex AI, AWS Bedrock, and Anyscale. For Google Vertex AI, at that time in 2024, we should have set up a dedicated GKE cluster. So that was not really simple to set up and to operate. It's another piece of infrastructure for us. For AWS Bedrock, again in 2024, the solution was quite new. The solution with Bedrock to use private model and LoRa adapters, and the pricing at that time was not really clear. That's why we have chosen to do a proof of concept with Anyscale. So the objective was simple: assess the cost effectiveness compared to OpenAI GPT models, evaluate the reliability and scalability, and experiment with multiple LoRa adapters and benchmark the performance compared to the base model. To do that proof of concept, it was really simple. We set up a array cluster with one base model. It was LLaMa 3.1 8 billion. We put 3 distinct LoRa adapters that were fine-tuned by our data science team. And the configuration was from minimum 1 GPU to maximum 10 GPU with autoscaling enabled. And we used 10,000 prompts given by our data scientists too for each LoRa adapter, and we load tested. We made multiple load tests during 1 hour. So we want to measure the input and output token per second to extrapolate the real pricing at production scale. And we want also to monitor the scaling up and down of the worker in the cluster. So just a quick slide to explain how does it work with LoRa adapter and during the load testing. So to load test, we use an HTTP load test tool. And the request is look like this. we pass the base model, that is always LLaMa 3.18 billion. Then for each LoRa, we pass also the LoRa adapter for each LoRa adapter we want to test. In the array cluster, on the worker node, the base model is downloaded during startup from Hugging Face. Then the adapter are lazily loading, meaning they are loaded and downloaded and loaded into memory only during the first request. So the results were promising. We tested firstly with one node. We had 4,000 input tokens per second and more than 400 output tokens per second. And when we increased the maximum number of nodes, the performance were stable. We had a latency from 2 to 4 minutes when a new node is spinning up. And for the LoRa adapter, the overhead was less than 5% compared to base model, so it's okay. And the lazy loading is negligible. The lazy loading into the downloading, the lazy loading into memory is negligible. So to conclude this POC, the price estimation was 3 times less with this Anyscale cluster with LoRa adapter and LLaMa 3 8 billion than the GPT-4o mini model. So lazy loading was working well, the autoscaling too, and in that case, it works because the array cluster and the array queue acts as a buffer for handling the workload spikes while we are waiting for new node to start. Then later, when we've made more tests, we also added a client-side circuit breaker to make a back pressure mechanism when the workload became really too high, even for the array queue, So the POC was okay, and now from the POC to production, we started 3 array clusters because at Mirakl we work with what we call service classes. So service classes is a different type of environment, and each of your environment is really isolated from one to another. We have the alpha environment that is for the data engineers. It's to set up new cluster and to test new version of the cluster and the upgrade of the cluster. The second service class is beta. It's to validate the integration. It's like this cluster is used to make end-to-end tests, and it can be seen like a pre-production environment. And the last one, live, is for real data and real Mirakl customer workloads. For the deployment of LoRa adapters, it's quite simple. Our data scientists fine-tune the base model with their training data set on Hugging Face. Then the adapter is pushed on an S3 bucket, one S3 bucket for each service class, and then in the array cluster, the LLM could download the right adapter. For the Anyscale configuration, like I said, we want to run configuration as code. So the code is stored on a GitHub repository. Then we use GitHub Action plus the Anyscale CLI to provision and to update our Anyscale service or Anyscale array cluster. Some figures about what is on production today. Today, the average input token per second is more than 4,000, and the output is almost 200. It could seem really low, but in fact, our client, in fact, the sellers that are onboarding the catalog, doesn't use the service during by night. They don't try to set up the catalog by night. Majority of Mirakl customers are in Europe and in the US, and also during the weekend, nobody uses the service. So for the peak input, we got 80,000 tokens per second, input token per second, and more than 5,000 output token per second. The cluster, today the live cluster is configured to dynamically scale from 1 to 20 nodes, minimum 1 to maximum 20 nodes. And we are using L4 GPU. We are still using LLaMa 3, 3.1, 8 billion base model. And today in production, we have 7 LoRA adapters, one for each business use case for the catalog onboarding. So to sum up, thanks to Anyscale, and we have a manageable, cost-effective, and scalable solution today in production. Now we'll let Arthur continue.
So let's wrap a bit of this up. So with an architecture schema. So to take a step back and see where this all fits into the production pipeline of the catalog transformer, let's look at this schema. So basically, as we said, the catalog transformer is a sequence of different models that are going, for instance, to categorize, to extract attributes, to rewrite content, stuff like this. And what we've done is that we've separated the tasks and the models into 2 types of models. We have what we call the client-side models that are really lightweight and can be loaded from anywhere, which has basically all of the business logics. And everything that is compute intensive is deported into different endpoints that are accessed through APIs. So for instance, you can have GPU serving endpoints on Databricks, but you have also LLM hosting endpoints on our Anyscale private APIs. And basically, this allows us to centralize all of the compute that necessitates specialized hardware and to have a better efficiency in terms of computing. Because basically, you are going to have maybe 100 catalogs that are computed at the same time, so you don't want to set up 100 GPUs for that. And another great thing about this is that we can switch from Mistral or OpenAI APIs to Anyscale APIs very smoothly. And with the layering approach that I presented just before, this allows us also to test when we want to create a new inference type. So for instance, when we wanted to go in production with Anyscale, we were able to have a safety net with a backup system if the infrastructure was not following. And basically, this whole architecture allows us today, even with small volumes, to be quite confident in the scaling of the system, because today the catalog transformer is only accessible through, well, for a limited number of our clients, but we will increase the volume in the time, and this allows us to do a lot of things. And then what's next is, today we've talked about text-to-text use cases with LLMs. And we also have a lot of multimodal or even any-to-any use cases where, for instance, for an image, we want to extract a lot of metadata that then will serve as a building, as a first step to define, for instance, what are the processing steps to take this image and put it in a different way, or to characterize it for product acceptance and whatever. So basically, for this use case, it's image plus text to text. That's something we are already testing with Anyscale. And we also expect to have a lot of other use cases, such as image to image. And basically, our use of Anyscale comes down to this. We want the infrastructure to be as easy as possible for the data scientists to use, we don't want them to spend time for it. And we've seen this idea actually for a lot of presentation. And I think that's what we achieved today with Anyscale. Thank you.